Hello, a very warm welcome to everyone. I, Arunika Saxena, a master student under the guidance of Dr. Shirly Avargil, is presenting my research in front of you. The topic of my research is chemistry teachers' perceptions of models and students' conceptual models in the context of air quality learning unit. The research is funded by National Science Foundation and conducted at the University of Maine, US. In this slide, I'm giving brief introduction of academic content standards, a framework for K-12 science education and the next generation of science standards. These documents are developed by the National Research Council. The framework identifies major scientific concepts and practices essential for every student until the completion of high school for learning science. Some of the important practices mentioned in the framework are developing and using models, scientific inquiry, and engineering design. The research was conducted in a state that adopted the framework and the NGSS, next generation of science standards. My research is focused on the practice of developing and using scientific models. A framework for K-12 science education emphasis on representing phenomena by constructing diagrams, drawings, models, etc. Using of different type of modeling tools to explain a phenomenon. Refining a model to improve its quality and explanatory power. Running simulation through simple simulating tool for studying salient features of a system or a phenomena which are not visible to unaided eyes, for example, atomic structure, molecular bonding. What is an authentic scientific model? An authentic scientific model is a simplified, abstract representation of a system that highlights its central features explicitly. It is an essential part of a chemistry curriculum without which we cannot imagine teaching and learning of chemistry. It enables a student to generate prediction and help in explaining natural phenomena like condensation, evaporation, etc. It starts with producing an initial mental model and eventually developed into a conceptual model by students. The practice of developing and using scientific models in terms of learning process show students in models engage students in argumentation and scientific discussion from evidences. Models promote reflection on and clarification of existing ideas. Models used to test ideas and processes. Models help in obtaining, evaluating, and communicating information. On the other hand, the practice of developing and using scientific models in terms of teaching processes show models are strong pedagogical tools. Models can be used in learning progression to improve scientific ideas in students. Models can also accomplish educational goals such as conceptual understanding of a phenomenon. Why chemistry teachers teach with models? Chemistry teachers teach with models because learning progressions through model inform teachers about students' learning. Models assess student knowledge within a variety of representational levels of chemistry understanding, for example, macroscopic, microscopic, process, and symbolic. Models give insight into the way a teacher teaches chemistry in the classroom. Teachers can develop an interest of learning chemistry in students in the same way used by scientists to run their models. Teachers can also update students' knowledge through the iteration process of modeling. Why students should use scientific models and how their conceptual understanding enhanced by model. The practice of developing and using models leads to positive effects on students' attitudes towards science and problem-solving abilities. These practices also refine students' understanding of confusing and challenging topics in chemistry, such as NMR, spectroscopy, ionic equilibrium, and so on. Now I am presenting my research questions. In the presentation today, I will focus on my research question 1 and some results from the research question 2. Research question 1, what are teachers' perceptions of the scientific practice developing and using models and how they differ from the way it is described in a framework for K-12 science education? Research question 2, what are the characteristics of students' understanding of models and modeling in the context of the PBIS Air Quality Learning Unit? Research question 3, does and in what ways students' understanding of models and modeling associated with their teachers' perceptions of this scientific practice? Research performed in the context of project-based inquiry science PBIS Air Quality Unit. This learning unit is especially designed for 8th grade students in the United States. This learning unit is strongly aligned with a framework for K-12 science education as well as with the next generation of science standard. This learning unit teaches chemistry in the context of air quality. Some of the topics included in this unit are what substances make up air, what state of matter is air, how can chemical reaction be used to improve air quality in your surrounding. This learning unit also emphasizes on scientific inquiry along with developing and using models. Teachers and students both participated in the research. 17 middle school teachers participated. Out of 8 were interviewed from 5 different public schools of Northeast region of US. On the other hand, 450 8th grade middle school students from 10 different public schools of Northeast region of US participated in the research. Teaching and learning took place in the context of PBIS Air Quality Unit. Purposeful sampling is used for the selection of teachers and students in the research. In this slide, I'm showing teachers' demography. From the pie chart, we can see that 40% of teachers holding MA degree and 60% of teachers are holding BA. From the graph, we can see teachers having maximum years of teaching experience comes in the range of 21 to 30 years. Research tools used in the research regarding teachers are semi-structured interviews. The questions are based on the perceptions regarding developing and using model. Some examples are, what does it mean to teach with models? How do you use models in your classroom? Did you have a chance to think about models when you teach chemistry? Give examples. In what ways do models help the student to think about chemistry? Research tools used in the research regarding students are pre and post questionnaires given before and after learning the PBIS Air Quality Learning Unit. The questionnaires are model-based, selected from the American Association for the Advancement of Science project, which is related to the drawings and explaining a conceptual model of a chemical phenomenon. Example of close-ended and open-ended questions are given in the next slide. In this slide, I'm presenting example of close-ended question 1. A student draws a diagram that shows how he thinks water evaporates from a wet wash cloth sealed in a plastic bag. Based on the drawing, he predicts that if the wet washcloth is left sealed in the plastic bag for several hours, water will evaporate from the washcloth and it will dry out. When he tries this experiment with a real washcloth, it turns out that this prediction was incorrect and the washcloth is still wet. What should he do with his drawing? Note, question 1 also asks the explanation of the option chosen in the post questionnaire. Options are A. The drawing should be discarded and not used anymore to make predictions. B. The drawing should be changed so that it better represents what was actually observed with the real washcloth. C. The drawing should not be changed. D. The drawing should be used to make other predictions until one of the predictions turn out to be correct. I am giving you some time to think about the correct answer of the question. Yes, you are right. The correct answer of the question is B. The drawing should be changed so that it better represent what actually observed with the real washcloth. In this slide, I'm presenting other examples of close-ended questions. I'm giving you some time to get into the impression of these questions, and later I will tell you the right answers of these questions. The right answer of question number 2 is A. The right answer for question 3 is also A. The right answer for question number 4 is C. In this slide, I'm explaining by giving example about close-ended question 5. In a cup of liquid water, when would the water molecules stop moving? The correct answer here is D. The molecules would not stop moving in the cup of liquid water. In this slide, I am presenting example from open-ended question 6. You drink all the water from a plastic bottle. You put the cap on the bottle and tighten it. Then you put the bottle in the refrigerator. An hour later, you notice that the bottle is dented. Please draw what happened inside the bottle and then use your drawing to explain why the bottle dented after being cooled in the refrigerator. You can see that here two figures are given of the student's drawing. According to the figure 1, in the bottle 1, we can see molecules are further apart from each other. Later, in the same water, we can see that molecules are come closer, making the bottle dented. This drawing showing the conceptual understanding of model related with the phenomena of properties of gas. Our research is a mixed method approach. In qualitative data, interviews and 2 open-ended questions were analyzed by directed qualitative content approach. Categories were identified from a framework for K-12 science education and cross-checked by inter-rater agreement. In quantitative data, pre and post close-ended questionnaires were analyzed to assess students' conceptual understanding. First, we graded as correct or incorrect responses to 5 close-ended questions, and then later we apply descriptive as well as inferential statistics. In this slide, I'm showing findings from my research regarding teachers' perceptions of model. From the teacher's interview, we analyzed 179 quotations and 7 categories. Category 1, characteristics of model, is at its highest, that is 20.1%. Category 7 is at its lowest, that is 6.7%, which is used to assess learning. Findings regarding teachers' perceptions of model. For example, in the category 4, a student's ability to develop model, which describes successes and challenges faced by a student while developing models in the classroom. One teacher said, having them develop their own models to model things you cannot see or touch in some cases is kind of difficult. Things are so abstract that I think it's hard for them to model. Taking another example of category 7, used to assess learning, which describes assessing students' knowledge through models and identifying their misconceptions. Teachers said, I ask a student to create or explain models quite frequently as an assessment of their understanding. In this slide, you can see examples of categories: positive conceptualization, negative conceptualization, and as well as suggestions from the teachers. Taking the example of category 4, students' ability to develop model, we can see positive conceptualization show the process of developing models enhance the student's conceptual understanding. On the other hand, negative conceptualization show that abstract nature of chemistry make it challenging for a student to develop a model. One teacher also suggested that we should use different kind of model while teaching and learning chemistry. Taking another example from the category 7, used to assess learning, positive conceptualization show models are good as an assessment tool. But negative conceptualization show models do not provide a sense as much once they get dismantled or dispersed. One teacher suggested that we should make students feel comfortable with their drawings and do not grade them on the basis of art. Here, in this slide, I'm presenting findings regarding teachers' perception of developing and using models. We can see most of the categories are positive conceptualized. It means these categories are aligned with the framework. In this slide, I'm presenting findings regarding teachers' perceptions by category. This graph shows two important findings. First, from the category using a variety of models. We can see there is no negative conceptualization in this category because all teachers agree of using variety of models while teaching chemistry. Second finding we can see in the category used to assess learning. Here, very low quotations related with the model of assessment tool. But when teachers relate this category to model and assessment tool, they are positive. In actual, teachers did not conceptualize model as assessment tool. In this slide, I'm presenting findings regarding student conceptual understanding and modeling skills. We can see from the graph that there is significant differences in the pre and post questionnaire related questions 1, 2, and 4. Question number 2 and question number 4 show increase in post test because these questions are easy to the students. Question number 1 show decrease as compared to its pre-questionnaire test. Question number 5 show no significant difference in pre and post questionnaire test. In my next slide, I'm going to explain the reason behind the question number 1 and question number 5 because these questions are difficult for students in aspects of conceptual understanding. Here in this slide, I'm relating and explaining the decrease in the question number 1. The possible explanation for the decrease is that a student had to answer their choice and thus thought of choosing easier answers that will make them explain. That's why they choose option D, that is, the drawing should be used to make other predictions until one of the predictions turn out to be correct. It seems that the student do not understand that once they draw something, they need to change it to represent what actually happened when with the real washcloth. Here we are discussing about the question number 5. We can see that there is no change in pre and post responses. It is because the student did not make perceptions in pre and post because this question is difficult. It seems that they don't perceive model as something that a student need to change and revise. In this slide, I'm showing finding regarding conceptual understanding of a student and modeling skill. Examples of explanations from open-ended question 1 showing a student who opted option B explained his answer that if the washcloth is in a bag, no air can go into or out of the bag, making the washcloth stay wet. Another example of the student who opted option D explained that he should keep it because it will help him with other prediction. We can compare both the answer and understand that why students choose option D frequently. In this slide, I'm summarizing my finding regarding teachers' perceptions of model. Teachers perceive the practice of developing and using model as extending students' thinking about a phenomenon. It's challenging because every student has their own perspective of model and might understand and interpret it differently and accordingly, making a student bored and aloof when they need to go back to the same drawing for revision. It is necessary to be revised in order to develop the conceptual understanding. Teachers relate the practice of developing and using model as an assessment tool at its least. In this slide, I'm summarizing the findings regarding students' conceptual understanding and modeling skill. Teaching with air quality unit improved student understanding of models in question number 2 and 4 in the post questionnaire as compared to pre-questionnaire. Students choose easy option in close-ended question 1 because they were asked to explain the reason in their own words for their choice. In close-ended question 5, there is no difference in the responses of the pre and post questionnaire as the level of question seems complex for the 8th grade students. Our research aligned with the updated literature regarding the practice of developing and using models and emphasizes that construction and refinement of models encourage students to think deeply and imaginatively about scientific ideas. In the recent research, it was shown that the revision of models is the important aspect in learning chemistry because it reconstructs the understanding of a particular phenomenon. Teachers' perceptions of model as a tool for evaluation and assessment in learning progression is low, but their understanding is high. Another recent research shows that model and modeling practices are good instructional aids for teachers to monitor students' progress. Our research aligned with updated literature regarding the models and emphasized that learning abstract phenomenon of chemistry through models strengthened the conceptual understanding of student. We can see that in post-questionnaire, students' correct responses increase in question number 2, 3, and 4. In the recent research, it was shown that models as a tool help students to perceive conceptual understanding. We can also see from question number 1 and 5 that developing and using models make thinking visible and give teachers an insight into the current understanding and alternative ideas of students. Another research shows that models have great effect on prompting students' scientific views, especially in learning an abstract phenomena. My research also has some limitations. Relatively, for a short time, teachers had to teach the PBIS air quality unit. A specific population participated in research with very small diversity. My research showed theoretical as well as practical contribution. Theoretical contributions show a comparison of teachers' perceptions of developing and using models with a recent standard of framework for K-12 science education is unique. The comparison fills the gap between what teachers think about models and how it is conceptualized in a framework for K-12 science education. The research is distinctive in trying to connect teachers' perception of the practice developing and using model to the students' conceptual understanding. The practical contributions show designing professional development programs for teachers aiming at the practice of developing and using models as it is conceptualized in the framework. We are glad that most of the teachers and the categories align with the framework, but still there are some work to do in future. For example, teachers did not conceptualize model to assessment tool. Here, I recommend to examine perceptions of teachers with other practices in a framework for K-12 science education and their alignment. Foremost, I would like to express my sincere gratitude to my advisor, Dr. Shirly Avargil, for continuous support in my master's study and research. For her patience, motivation, enthusiasm, and immense knowledge. I would also like to give thanks to the Chemistry Education Research Group, especially to Dr. Gabby Schwartz and Yoram Zemel. We want to thank also to Professor Mitchell Bruce and Professor Francois Amir from the University of Maine for their advices and support in this research. Thank you once again.